Today we're going to talk about a part of the atom that we haven't really focused very much on so far this semester, and that is the electron. So far we've talked a lot about protons and neutrons, but electrons actually determine a lot of an atom's physical and chemical properties. So when we're talking about electrons, and also atoms and molecules in general, we're going to be talking about what we know as the quantum world. And that is the world of subatomic particles. And when I talk about subatomic, what I mean is the particles that make up atoms. So protons, neutrons, electrons, and other subatomic particles that we're not really going to go into detail in this class. And that is different from what we call the macroscopic world. And that is the world on the scale that we know. So that is what we could say the large scale world of everyday objects. And because these worlds are so different, matter just behaves so differently on different scales that we need to look at matter in two very different ways. And so the way that you're probably more used to thinking about is through classical mechanics. And if any of you are in physics this semester, or maybe took physics 1 last semester, this is probably what you studied. You probably studied some form of classical mechanics, and that is the physics that is used to describe the macroscopic world. So that's kind of like when you look at like forces interacting, how objects move, that kind of thing. And that might be a little bit different from what we're going to be talking about now, which is going to be quantum mechanics. And it's really cool. Matter just behaves so differently on a quantum scale that scientists needed to come up with a whole new form of physics just to explain what was going on. And that is what is now known as quantum mechanics. So that is the physics that are used to describe the world of subatomic particles. So, or used to describe matter on a subatomic scale. And it's important to distinguish between these because they're just so different. Matter just behaves so differently when you get down to the subatomic level, and it's really cool, but also very counterintuitive to what we're used to in our daily lives. So one scientist named Erwin Schrödinger decided that he wanted to kind of come up with a way to explain to people how quantum mechanics was so different from the classical mechanics that we're so familiar with. And he did that through the use of a thought experiment that we now know as Schrödinger's cat. So the thought experiment goes kind of like this. Imagine that you have a cat and it's locked in a box, and the box contains radioactive atoms. So when a particle, or when one of those radioactive atoms emits an energetic particle, it triggers a mechanism that causes a flask of cyanide to break, which would then kill the cat. But because we can't observe what is going on inside of the box, the cat is both alive and dead at the same time. And only when we open the box do we force the cat to be either alive or dead by observing it. So that's really crazy, right? Like we know a cat can't be both alive and dead at the same time. That is just not physically possible. The cat cannot be in two states at once. And like what Schrödinger was saying is it's not that like, oh, well, maybe the cat was alive, maybe it was dead, we just don't know. In this thought experiment, the cat is literally both alive and dead. That's crazy because we know that in the world that we're really used to, that just isn't possible. But on the quantum scale, that's how electrons can behave. Electrons can be in two different states at once. We just can't observe them being in two different states at once. So also, this little cat over here, that guy's my friend's cat. His name is Schrödinger, so he is Schrödinger the cat. He is the best science companion that you could ever hope to meet. So, anyway, the reason that we want to talk about light, as I'm sure you've seen from your reading, is that electrons and light have a lot in common. So we can actually learn a lot about how electrons behave by studying the nature of light. And one of these properties that electrons and light both have in common are what we know as wave-particle duality. And that is that electrons and light both have some properties of waves and some properties of particles. So we can look at the wave and particle nature of light to learn more about the wave and particle nature of electrons themselves. So we're going to start by looking at just the wave nature of light. So light is a form of electromagnetic radiation. Oops. Electromagnetic radiation. What is that? It is basically just like the energy of oscillating electric and magnetic fields. And we can study this light, this electromagnetic radiation, and by doing so, we learn a lot about how electrons behave as well. So the first thing that we want to do is kind of learn a little bit about like what is a wave. So waves have some different characteristics. One of them is the wavelength. And as you can see here, the wavelength is the distance from crest to crest. So the crest is like these little top parts right here. So that is a wavelength. You could also define it as the distance from trough to trough. So the troughs are the lower parts of the wave. And that distance is going to be equivalent to each other. They're going to be the same. And so wavelength defines the color of that wave, at least in the visible spectrum that we can see. And these are going to be measured in units of distance. Wavelength. And by units of distance, I usually mean like meters, centimeters, nanometers, anything along those lines. Another property that waves have is amplitude. And amplitude is what we visually could see as the height of the wave, at least if we are using this representation. So that would be the amplitude of this wave right here. And the amplitude determines brightness, how bright that light is. Another property that is very important is the frequency. And frequency is going to be the speed of the wave. And so by speed of the wave, I mean the way we usually look at that is the number of crests that pass a stationary point per units of seconds. So that means that the units of frequency are going to be 1/seconds, which is the same as seconds to the negative first power. And frequency and wavelength are related. So frequency and wavelength are inversely proportional to each other. So that means that something that has a shorter wavelength is going to have a higher frequency. And there's an equation that we can use to determine the relationship between those. And here's that equation. So we have nu equals c over lambda. So this value here is our frequency. This value is our wavelength. And this c here is the speed of light in a vacuum. And that's a constant. So that that's going to be the same value every time you use it. So that is 3.00 times 10 to the 8th meters per second. And that's the equation that we can use to determine the frequency if we know the wavelength, or we can determine the wavelength if we know the frequency. So let's go ahead and use that equation to do a practice problem. So this problem asks us to calculate the wavelength in nanometers, so that's important, those are our units, of the red light emitted by a barcode scanner with a frequency of 4.62 times 10 to the 14th 1 over seconds. So again, look at our units. Those are going to be the units of frequency. So we have our equation here. And so we can use what we already know to substitute into those values. So we know the frequency. So we know that the frequency is 4.62 times 10 to the 14th. And I'm going to kind of switch up the format of these units a little bit so you get used to seeing it both ways. So I'm going to write it this time as seconds to the -1. Remember that that is the same thing as 1 over seconds. And that is going to be equal to 3.00 times 10 to the 8th meters over seconds over lambda. So when we solve that math, I will go ahead and give you a second to solve that. You can pause the video if you want. But when we solve that, you should get 6.49 times 10 to the -7th meters. But what is our question asking? It's asking for the wavelength in nanometers. So that means we're going to have to do a dimensional analysis conversion. So let's go ahead over here to the side and do that conversion. Oops, sorry. So we have 6.49 times 10 to the -7th meters. And we know that there are 10 to the -9th meters in 1 nanometer. So go ahead and do that conversion. And you should get 649 nanometers. So that is our wavelength of red light that is emitted by a barcode scanner. So let's go ahead and take a look at our electromagnetic spectrum, see where that actually falls. So 649, like that falls right in this area here, which is the visible region. And if we look even closer at that, that's like right around there. So right in that like reddish orangish area. So that makes sense, right? Like we have a reasonable answer because we got an answer that is kind of like a reddish color light. You don't have to memorize this chart, but I would recommend having a general understanding of the scale at which all of the different types of light are on. So we have their visible spectrum from 400 to 750 nanometers. And then the ultraviolet is on a slightly smaller wavelength, so on the scale of like 10 to the -7th to 10 to the -8-ish. And then X-rays have an even smaller wavelength, and gamma rays have an even smaller wavelength than that. On the other side, we have the infrared region here. So This is as our wavelength gets larger and larger, we go into the infrared, microwave, radio wave. So again, you don't need to memorize the exact numbers of this whole chart, but you should have a fairly good understanding of where the different types of light all fall on this chart. Another property of light that we're going to want to talk about if we want to understand electron behavior is interference. And interference works like this. Imagine that we have two waves and they're overlapping with each other. So here's one of our waves, and here's a second wave. And the crests are going to line up with the crests, and the troughs are going to line up with the troughs. So when that happens, they're going to amplify each other. And they're going to combine so that the amplitude is increased. And this is what is called constructive interference. And that is when the waves are in phase with each other. But alternatively, let's take a look at what's going to happen if the waves are not in phase. So let's say here's our first wave. And then instead of the crests lining up with the crests and the troughs lining up with the troughs, let's say that our waves are out of phase. So our crests are going to line up with the troughs, and the troughs are going to line up with the crests. When that happens, the waves are actually going to cancel each other out. So rather than making a bigger wave, it is going to lead to not having a wave at all. And that is called destructive interference. And that occurs when the waves are out of phase. And this is a really important concept because this is going to let us learn a little bit more about electron behavior. So when scientists were trying to figure out how electrons behave, they did this absolutely brilliant experiment that we now know as the double slit experiment. So what you would expect, let's say that you were shining a beam of electrons at a wall through two different slits. So let's say here's your wall, and there's two slits in this wall, and they were going to hit somewhere over here. Let's make our electrons shiny. So if electrons were behaving like particles, we would expect them here to go through the slits over here on this side and just hit the wall, hit this wall behind the slits. But if we shined the electrons over here, they wouldn't pass through. They would only pass through where we had the slits. So what you would expect is to have two little regions of light there and there. But when scientists actually did this experiment, that's not what they saw. They saw what is known as an interference pattern. So they saw alternating light and dark spots. And what that told them is that, in fact, the electrons were not behaving as particles like would have been expecting. They were behaving as waves, which was completely mind-boggling because you think of electrons as particles. You don't think of electrons as waves. So by doing this experiment, scientists were able to learn a lot more about electron behavior. So this double slit experiment showed that electrons can actually behave as waves. So that's really crazy. And the fact that electrons can behave as waves leads us to be able to make some more, assumptions or be able to do more calculations and get to know the nature of electrons a little bit better. So if electrons can behave as waves, that means that electrons themselves should have a wavelength. So again, that's really weird to think about because we're so used to thinking about electrons as particles, but we can actually measure the wavelength of an electron, and that's known as the de Broglie wavelength. So that, again, is the wavelength of an electron. And we have an equation for that. It looks like this. So notice that this time this V here is actually a V. This time it actually stands for velocity, not necessarily frequency, and the velocity is going to be in units of usually meters per second. This m here is going to be mass, and that mass is going to be in kilograms. So remember that grams is actually not the SI unit of measurement. The SI unit of measurement for mass is actually kilograms. And then we have our wavelength in meters. And Planck's constant. And that value is 6.626 times 10 to the negative 34th joules times seconds. And that is a constant that that's the value that h is always going to be. So how do we use this equation? Let's take a look. So if we want to calculate the wavelength of an electron traveling at a speed of 2.65 times 10 to the 6 meters per second, you can go ahead and use our equation. We know that speed and velocity are the same thing, so that's going to be our v. Wavelength is what we're trying to find, so that leaves our h and our m. The m value is given, that is our mass, and then h is always a constant, so we have that value already. So we have wavelength equals h, 6.626 times 10 to the negative 34th. We know the units are joules per seconds. We also know that we want to end in units of meters. So how are we going to do that? How are we going to cancel joules? Well, remember from earlier in the semester, joules are actually the same thing as kilograms times meters squared over seconds squared. So that is the same thing as joules, and then times seconds. Then multiply or divide that by the mass of an electron in kilograms multiplied by the velocity. Okay, so now we get to start canceling units. So one of these seconds will cancel with this seconds will cancel with this seconds, one of these meters will cancel with meters, kilograms cancels with kilograms. And go ahead and pause the video if you want to take a second to solve this out on your own. And then the answer should be 2.74 times 10 to the negative 10th meters. Okay, so that was a little bit about the nature of electrons and in particular the wave nature of light and electrons. Um, I'm going to switch over to another video to talk about the particle nature of light and electrons.